For this lab, I decided to record myself throwing a volleyball into the air in order to demonstrate a variety of physics principles. First, this would allow us to showcase Newton's second law, which consists of the momentum principle, which is that delta P is equal to F net times delta T, and principles related to predicting the future motion of the volleyball, which is delta V over delta T equals F net over M. Additionally, I use this demonstration in order to showcase the energy principle, which consists of the conservation of energy, which is that delta E is equal to delta gravitational potential energy plus delta K, which is the kinetic energy. Kinetic energy is equal to 1/2 mv squared, and gravitational potential energy is mg delta y. And this will be demonstrated in my code, which I will talk about in a second. So first, I loaded a video of me throwing the volleyball into the air into Tracker, and in order to do this, I set the calibration stick equal to 1.57 meters, which was my height, and I set the coordinate axis with the center of the ball as the origin, with the positive x direction going right and the positive y direction going up, because that's how the motion of my ball went. So the way that the video went was that the ball went up and came back down, and so the tracker followed the center of the mass and recorded the motion, which you can see in these graphs over here. So we have one in the x direction and one in the y direction, and as you can see, the one in the y direction seems like a much more accurate portrayal of the motion of the ball as showcased in my video. And then additionally, I also had the x and y values based on the time over here as well. So some changes that I made to my code, which I will show in relation to the code in a second, but overall I set the mass of the ball equal to 0.26 kilograms, which was the weight that I found. I set the initial position based on the tracker data. I set the initial velocity equal, I had to calculate the initial velocity at t equals 0.067 seconds and t equals 0.1 seconds. And so in the x direction, that was equal to 5.45, and in the y direction, that was equal to 7.57 meters per second. The net force was equal to the gravitational force plus the drag force. And so as we know, the gravitational force is equal to the regular force times capital G, and the drag force is equal to negative b times the velocity. And in this case, my b was equal to 0.005. And then I also had to calculate the overall change in motion and the energy change, which I had eventually plotted in terms of the change of energy. So we can see these changes in my code over here. Over here, I had to change the mass of the ball. Additionally, I changed the position and the velocity of the ball, which I had to calculate, and then the position was found through Tracker. I used my proportionality constant that I calculated, and then over here, I put in the how to calculate the kinetic energy as well as the gravitational potential energy. And then over here, I did all this in terms of the t that I found when I was throwing the ball. And I defined the initial energies as the kinetic energy and gravitational potential energy, and then showed how to use gravitational force. And then these equations over here basically calculate the position and velocity of the ball at each time, and then also predict the new position, which you can see over here. And then after that, I had to calculate the energy changes, which I did by calculating the overall kinetic energy and then the delta K, which is the change in kinetic energy, and then the gravitational potential energy. And then I used the energy principle to show that the kinetic energy was plus the gravitational potential energy. And then all these equations were used to graph and plot the different energies, which we can see over here. This was the final graph that I got, which just raised the motion of the ball. And then over here, I actually displayed all four motions of the ball, so the actual x and the actual y based on Tracker, and the model x and the model y, which I got based off my code. And so you can see the major differences in those. And then I also calculated the energy changes, so you can see the different energy changes over here. So green was the change in energy, which is very, very close to zero, but it's not equal to zero, which means that energy is not conserved, meaning that other energy was probably being used at some point during this case. But over here, you can also see the differences in the kinetic energy and the gravitational potential energy. So overall, my results show that the ball goes below the x-axis because it falls lower than the position that I originally set the origin at, since it hits the ground. And then as you could see in my graphs that compared all four of the motions based in the Tracker and in the code and the x and y positions, the dotted blue line was significantly different than the other lines, which could have been because the initial velocity in the x direction was too fast in the positive x direction, since the ball went backwards from where it was originally hit, and then went forwards before falling, which was not captured in the model data, or the Tracker points might have been off. So those are some sources of error that could have been possible. And additionally, I discussed this, that energy was not conserved, as we saw in the graph of the change in energy, because the sum of the kinetic energy and gravitational potential energy was not equal to 0, which means that energy was being used elsewhere. Thank you.